Section 3.3, Measures of Relative Standing and Box Plots. This section introduces measures of relative standing, which are numbers showing the location of data values relative to the other values within the same data set. The most important concept in this section is the z-score. We'll also discuss percentiles, quartiles, and box plots. So a z-score, which is also called a standard score or a standardized value, is the number of standard deviations that a given value x is above or below the mean, and it's calculated using one of these formulas. For the sample, we take the distance between the data value and the sample mean and divide by the standard deviation of the sample. For the population, we take the distance between the data value and the population mean and divide by the population standard deviation. And we round z-scores to 2 decimal places. Important properties of z-scores. A z-score is the number of standard deviations that a given data value is above or below the mean. Z-scores are expressed as numbers with no units of measure. A data value is significantly low if its z-score is less than or equal to -2, or the value is significantly high if the z-score is greater than or equal to +2. If an individual data value is less than the mean, its corresponding z-score is negative. Conversely, if it's above the mean, the z-score will be positive. Which of the following 2 data values is more extreme relative to the data set from which it came? The 400-gram weight of a newborn baby among 400 weights with a sample mean of 3,152 grams and a sample standard deviation of 693.4 grams, or 99-degree Fahrenheit temperature of an adult among 106 adults with a sample mean of 98.2 degrees Fahrenheit and sample standard deviation of 0.62 degrees Fahrenheit. So what we can do is standardize each of these relative to the distribution from which they were drawn and then compare the z-scores. So for the 400-gram birth weight, we're going to take the data value 400, subtract the mean of the sample, and divide by the sample standard deviation, and we come up with a z-score of 1.22. For the body temperature, same thing, and here we come up with a z-score of 1.29. The higher the z-score is, the further from the mean or the more extreme the data value is. So these z-scores show that the 400-gram birth weight is 1.22 standard deviations above the mean, while the 99-degree Fahrenheit body temperature is 1.29 standard deviations above the mean. Because the body temperature is further above the mean, it is a more extreme value. And here's a little graphic, and we've looked at this before. Significant values are going to be those that are either lower than, have a z-score at -2 or less, or have a z-score of +2 or more. The lowest platelet count in a data set is 75. Is the value significantly low? Assume that platelet counts have a mean of 239.4 and a standard deviation of 64.2. So again, we're going to convert that platelet count of 75 to a z-score. We subtract the sample mean, divide by the standard deviation, and we get a z-score of -2.56, which is very low. And so this is below the -2 z-score, so therefore we say that this platelet count is significantly low. And low platelet counts are called thrombocytopenia. We can also calculate the platelet counts that have a z-score of -2 and +2 and assume that a platelet count, again, has that mean of 239.4 and a standard deviation of 64.2. I want to mention also, you're going to have to do these calculations on a calculator. StatCrunch won't do this type of a calculation. So for the z-score of -2, I take the mean of the platelet counts and I subtract 2 standard deviations and I get 111. And notice my platelet count of 75 is indeed below that. And then on the significantly high side, I get a platelet count of 367.8. So platelet counts less than 111 or greater than 367.8 are significant. Platelet counts between those 2 values would be considered not significant. Percentiles are measures of location, and they're denoted P1 through P99, and they divide a set of data into 100 groups with about 1% of the values in each group. The process of finding a percentile that corresponds to a particular data value is given by this formula. The number of data values less than the data value of interest, divide by the total number of data values in the data set, and then multiply by 100. So we're going to use the Verizon cell phone data speeds. These are accessible through my stat lab using the StatCrunch option, data sets from the textbook, and it's called Airport Speeds. and we want to find the percentile for the speed of 11.8. So these are in order. I'm going to use the data set in StatCrunch, and I notice I put them in order, and I notice that 11.8 would fall right here at observation 21. So there's 20 data values less than 11.8. So we take 20 and divide by 50 and then multiply by 100, and we get a percentile of 40. So 11.8 is at the 40th percentile for this data set. And this is the number that separates the lowest 40% from the highest 60% of the data values. And we write it with this notation right here, capital P, subscript, the percentile that we're calculating, and then we give the value on the other side of the equal sign. All right, if we want to go the other way, which is to find a particular percentile in a data set, your textbook gives a manual way to do it. I'm going to stress that we're going to use StatCrunch. It's much, much easier. So we want to take that same data speed data set that we were just using. We want to find the 62nd percentile. And I've got the data values in order here. So in StatCrunch, you simply use stats, summary stats column, select the column, and in the percentile area, right down here below where you pick the statistics, put in this percentile that you want. You can put in more than one. We're going to put in 62. And so here's my output. So the 62nd percentile for that data set is 15.65. Quartiles are measures of location also denoted as Q1, Q2, and Q3. They divide a set of data into 4 groups with about 25% in each group. The first quartile is also called P25. It separates the bottom 25% of the sorted values from the top 75%. Q2 is the median, P50, separates the bottom 50% from the top 50%. And then Q3 is the same as P75. It separates the bottom 75% of the sorted values from the top 25%. And there's no universal agreement on the procedure for finding percentiles. So therefore, if you use different technologies, you may get different answers, and don't worry about it. They're going to be fairly close. Some other statistics that are used, defined using quartiles: the interquartile range, which is a measure of variation, difference between Q3 and Q1. The semi-quartile range, shown there, the mid-quartile range, and finally the 10 to 90 quartile range. So some other statistics that statisticians may use. The 5-number summary for a set of data consists of these 5 values: the minimum, the first quartile, the median, the third quartile, and the maximum. And we're going to find a 5-number summary for that cell phone data again. And I'm going to use StatCrunch. And because they're sorted, we can see the minimum and the maximum from the table right here. The minimum is 0.8 and the maximum is 77.8. But I'm going to use StatCrunch, and I'm going to select the statistics that I want. And if I put them in order, they'll come out in the order that I want. The minimum over here, min, then I selected Q1, the median, Q3, and the maximum. And here's my output. And so the minimum here is 0.8. Quartile 1 is 7.9, the median is 13.9, Q3 is 21.5, and the maximum is 77.8. Now we can use those 5 numbers to create a picture of the data called a box plot. And it's a graph consisting of a line extending from the minimum to the maximum with a box drawn with lines at the first quartile, the median, and the third quartile. And here's a manual method. I'm going to urge you to use StatCrunch to do this. It's much easier. So we're going to use that data speed again. Here's the one from the textbook that they did by hand. They've labeled it actually with the minimum, Q1, Q3, Q2, Q3, and the maximum. And in StatCrunch, I go under Graph, Box Plot, select the column. Under Other Options, right now I'm going to just choose to do the boxes horizontally so it looks somewhat similar to the one in the textbook. And here's my box plot. Now, skewness can also be identified on a box plot, and also outliers. A distribution of data is skewed if it's not symmetric and extends more to one side than the other. We talked about this earlier. And again, I'm going to click through this because we're going to use StatCrunch to do the modified box plot. And in that options section right here, you're going to make sure this first option is checked. Use fences to identify outliers. And so for that data speed, there actually are 4 outliers up here on the high side. And you can see the skewness actually. You see how long the tail would be here if we did a histogram. So there's 4 outliers. And in the data set, I can identify those as 43, 55.6, 71.3, and 77.8. And for this section, because we cover quite a few concepts, there's 3 different StatCrunch videos that you may want to take a look at to help you as you're working on your homework.